Okay. We prefer the use of distance protection because the fundamental of the distance protection is using the ratio between voltage and current. Okay. And that is extremely helpful because avoids some of the drawbacks coming from the overcurrent and grading. Okay. But another thing that is extremely important is that the distant relay also have some limitations and there are some characteristic aspects. And one of them is that we need to take care about the voltage that is at the relay point, and that voltage, I mean, we cannot have zero voltage at the terminal. We can have it. There is a mechanism called memory, but in theory we don't want to have zero voltage at the terminals of the relay, because terminal voltage will make the relay failing to understand what is the location of the fault. Okay. And also a very low voltages at the terminal relay, at the distant relay, can create some problems. And that is the reason that we need to take care about something that is called the source impedance line impedance ratio. Okay. um, because if you remember, the voltage can be obtained by something that we call the voltage divider. Okay. And the voltage divider is basically depending on the ratio between the impedance in the series connection. Okay. What I'm trying to say is, let's consider this very basic example. We have bus bar A and B. There is a transmission line over there. There is a transmission line. You can see the impedance over there. And there is a relay over there. And that relay have a current transformer and also a voltage transformer. Okay, it's not depicted over there, but we have also a voltage transformer, and the voltage transformer is having a voltage over here at the location of the relay. Okay, let's assume that the voltage that is coming from the impedance is the voltage P. Okay, and let's say that is the voltage that we can see here at this single line diagram over there. Okay. Okay, all my students, they are quite clever in terms of circuit analysis. And imagine now that we have here a three-phase short circuit, as we are presenting here. We have here a three-phase short circuit. Okay. If we have a three-phase short circuit over here, this voltage should be zero, and we are closing the loop. And the current that the relay will take measurements, it will be the short circuit current. Okay. And the short circuit current will be the voltage divided by the total impedance. Okay. However, I don't care about the short circuit current at this moment. What I am looking for here is about the voltage at the terminals of the relay. Okay. And using voltage divider rule, a modified version of the voltage divider rule, what we can see something here is very important. We can define the voltage at the terminals of the relay like depend, it's proportional to the voltage, to the supply voltage, but depend of this number over here in the denominator. And the number that I care is this ratio. What is this ratio? Well, as you can see, ZS is the source impedance, and in the denominator, you can find ZL, and that is the impedance coming from the line, okay? And that number, the ratio between the source and the impedance, that is what is defining the voltage at the relay location, okay? What I will do now is, okay, let me take this equation. Let me take this equation, and now let me plot this equation, okay? Over there, what you can see is a plot of the voltage at the terminal location or the relay location in percentage of the rate voltage, okay? That is this voltage VR, okay? We can say that that is per unit referred to the rate or nominal voltage. And what you can see on the horizontal axis, is the ratio between the source impedance and the reactance, and the line impedance. And as you can see over here, I use a linear axis on the voltage, and for the horizontal axis, I using a logarithmic scale. Okay, what is the idea here? I would like to show you that if the ratio between impedance and line is very small, the voltage is quite high at the terminals of the relay. But if we go to larger ratio between source and line impedance, you can see how the voltage decrease so much. I mean, over here is 9%, and that is the starting point over here. That is very low voltage at the terminal of the relay, okay? What I need that you understand is this plot over here is coming from this equation. And this equation is basically defining the terminal voltage at the relay during a three-phase fault condition, okay? But now the question is, what's happening if instead of having a three-phase fault that all my power system analysis students must know that that is a symmetrical fault? What's happening if we have a fault that is involving ground or earth? I mean, for instance, a double line to ground, or if we have a line to line or line to neutral fault, okay? Well, if we have a line to line, there is no problem. We can keep using the same equation as you can see here on the right, with the main difference that we need to use is the line to line voltage. But if we have a line to neutral voltage, the situation starts to be a bit more complicated. Because if you remember from power system analysis, when we have a single line to ground fault, we have negative and zero sequence circulating inside the system. And as consequence, I will not make the deduction, but any one of my very clever students, they can make the calculations. And what you can see over there is that the voltage at the terminals of the relay, they are affected by the ratio between zero and positive sequence impedance, okay? What I want that you understand is those equations are extremely helpful if you need to calculate what is the voltage at the relay location during a three-phase fault or line-to-line fault or line-to-neutral fault, okay? Okay, now we are moving forward. The distant relay right now, it's basically a device that is not only supervising and controlling and detecting abnormal conditions, fault conditions at the distance or impedance. Okay, modern numerical relays, they are extremely good because right now they are able to combine many features at the same time. Okay, in a modern numerical relay, you will find that the relay is doing many things. Starting from the fault location, that is the distance between the relay and the possible fault location. instantaneous overcurrent protection, but it's also doing many other things like CT supervision, check synchronizing, auto reclose, circuit breaker, state monitoring and condition control, measurement for voltage and currents, event recorder, disturbance recorder. I mean, right now, a distant relay is extremely helpful because in a single device, you can found so many functionalities, okay? Well, but I need to keep talking about the importance of the source impedance at the to define the voltage at the relay location, okay? What I want to introduce right now is the concept of something that is called the source impedance ratio, okay? Few slides ago, I introduced and I say to you that the voltage at the relay location is extremely important because it's define the capability of the relay to identify faults, okay? And there is a classical term to define the ratio between the source impedance and the line impedance, and that is the SIR or source impedance ratio, okay? Um, if you are familiar with the IEEE standard C37113, you can find over there the full definition of the source impedance ratio. But in simple terms, is the ratio between the source impedance and the line impedance, okay? And the standard, again, the C37.113 use the SIR use the source impedance ratio to identify three different set of transmission lines. We can define long transmission line when we have a source impedance ratio that is below of zero point 0.5. And we can say that we are in a short line when the source impedance ratio is larger than 4. If we are between 4 and zero point 0.5, that is a middle line, okay? But probably you are wondering, okay, what is the implication? What is the important point of knowing the source impedance ratio? Okay, the source impedance ratio is very important because it will allow you to identify what is the voltage drop at the relay location when you have a fault at the transmission line. For instance, if you can see over here on, you can see that in this case, I have a short line. And in this case, the source impedance ratio is 4. What this indicator is saying is that the source impedance is probably 4 times bigger than the transmission line. As a consequence, if a fault happens on the transmission line, there is a big voltage drop across the source impedance. And for instance, for this case, a source impedance ratio will create a voltage across the terminals of this relay of 20% of the rate voltage. That is something quite relevant. But on the other case, look over here, we have a case that we have a long transmission line. In this case, the transmission line, the source impedance ratio is zero point 0.5. That means, for instance, that if we have a source impedance of zero point 0.5, the line will have 1. But the important aspect here is what will be the voltage, at the relay location. And in this case, because we have uh, uh, a relative long transmission line and we have more impedance at the line, in this case, we will have a relative high voltage. You can see that is around 66, 67% of the rate voltage. Okay. Okay. Um, Let me put some numbers in this source impedance ratio. Okay. Let's run a numerical example, very short numerical example about source impedance ratio. Okay. In this case, imagine that we have a 500 kV kilovolts line and the positive sequence is around 0.332 ohms per kilometers. Okay. We know the positive sequence reactance in ohms per kilometers. Okay. And in this case, we know that we have an impedance source, and this impedance source is zero point 0.1 per unit, zero point 0.1 per unit, but this is representing a 10,000 MVA source, okay? Now, the question is, what is the length limit for short lines and long lines, okay? And in this case, we want to run all the calculations in per unit system using 100 MVA as a base, and the voltage base is 500 kilovolts. Okay. Okay, the solution is very simple. The first step is we know that the impedance, external impedance, is 0.01. And now what we want to do is calculate the base impedance, okay? The base impedance is using the equation. My students are quite clever in power system analysis. Depend of the square value of the base voltage and divide by the apparent power base, okay? And we obtain over here, there is a impedance base of 2,500, okay? Next step, we want to know what is the impedance in per unit per kilometers of this 500 kV transmission line. And it's very simple. We know that the impedance is 0.332 ohms per kilometer. We divide by the base that is 2,500, and we got that small number over there of 0.0001328. Okay, what is the next step? Okay, we want to identify the difference between short lines and long lines. And the difference between short lines and long lines is defined by the source impedance ratio, okay? And for short lines, the source impedance ratio must be above 4. What I'm trying to say, if we are working with short lines, the source impedance divided by the line impedance must be bigger than 4, or in other words, the transmission line must be less than the source impedance divided by 4, okay? But what we want is not the total impedance in ohms. What we are looking is for the length that is defining a short line. What we need to remember is that we can say that the total impedance of the transmission line is the product of the per unit kilometers multiplied by the length in kilometers, okay? And from there, we put inside this equation over here. Now we are using lower letter Z, and that represent per unit per kilometers, and the letter L represent the length, okay? When we put this equation into the other, we can identify that a transmission line will be short if it's below the source impedance divided by 4 times the line impedance in per unit per kilometers, okay? Now, when we put the number together, this is the interesting result. Now we have that if any line have a length that is below 18.82 kilometers, if we have any transmission line with that specific impedance per kilometer, if we have a 500 kV transmission line with that very specific parameters, anything that is shorter than 18.82 kilometers, that is a short line, okay? Then we can do the same numbers, and in this case, what we want to do is, instead of short lines, we are interested in long lines, and the IEEE C 37113, and that is the IEEE Guide for Protective Relay Application of Transmission Lines, say is that any long line has a source impedance ratio that is below 0.5. And what we are doing here again is just playing with the equations and using the impedance, the line impedance in per unit per kilometers. And doing so, we obtain over here that any transmission line above 150.6 kilometer, any transmission line 500 kV transmission line with a length above 150.6 kilometers, it will be identified as a long transmission line. Okay.